Okay, the next talk will be by Ashley Stevens from Arteris, and he will talk about the topic optimizing data transport architectures in RISC-V SoCs for AI and ML applications.
Yeah, hi, I'm Ashley Stevens. I'm a Director of Product Management at Arteris. So I'm going to talk about some of the challenges of building RISC-V AI ML SoCs. First one is diverse interface protocols. So RISC-V is a very diverse, very active ecosystem, which is good, but it also makes it more difficult when you find out that there are so many differences in the hardware side of things. You have varying coherency models, or not at all. And then in AI, you have the issue with just memory bandwidth. A lot of things that we get involved in AI are also automotive, just mentioned automotive in Munich. And so you have additional issues, standards for functional safety, and then you get into verification and implementation. So this diagram shows a typical system-on-chip with Arteris IP, and there's really two main products to consider, and they are Arteris Encor, which is a coherent interconnect, and Arteris FlexLink, which is a non-coherent interconnect. And really, a lot of this talk is about understanding where and when to use each of those products within the system. So the Encor coherent interconnect is designed to support multiple protocols for coherency. So as well as supporting CHI-B, CHI-E, it also supports ACE, Amber ACE, and the interoperable. So what that means is that within the interconnect, we have our own coherency protocol, and there are network interface units that convert from an external protocol, such as CHI or ACE, to our internal protocol. So that means you can easily create additional network interface units that convert to the Arteris protocol, which is very generic, and can support MESI or MoSI coherency protocols, for example. So it's not tied to any one particular processor or architecture. It can work with RISC-V, it can work with ARM. In theory, I think it could work with both at the same time, but we haven't proven it. No one really is motivated to try to do that, to work with the enemy. Supports multiple I/O interfaces, ACE-Lite, AXI, and this optional Proxy Cache, which I'll come into, which is quite interesting for integrated accelerators. Then you have the usual interfaces, and there's a directories and filters. So why would you use CHI and ACE in the same system? Well, as I mentioned, the RISC-V community is very dynamic. You have what I see is the newer processors, the more advanced ones, tending to go to CHI. Some of the older ones use an ACE. So you can actually interoperate between the two with a mixed CHI-ACE system. It also means you can leverage investment in your ACE IP. So maybe you've used ACE before. You can reuse it, but also use it with a new processor that uses CHI. Or maybe you have an older real-time processor that you want to use along with a newer application processor using CHI. And as I said, the proxy caches help to ease the integration of non-coherent accelerators. So when you have an accelerator in the system, these things can do all sorts of different transactions. They can do long bursts, they can do short bursts, they can do things with sparse byte lane strobes. And these things are quite tricky to integrate into a coherent system, which operates on a 64-byte or 512-bit coherency granule cache line. What the proxy cache does is it acts as a cache between these I/O initiators, DMA devices, and the memory system, and caches the traffic. That kind of also regularizes the traffic as well, because it will ensure that what's seen in the system is only 64-byte coherency granule transactions. So the proxy cache itself is configurable. It says up to 8 megabyte. Typically, they're quite small, actually, 64K, 128K. And so what you'll see is not only a reduction in bandwidth in the coherent system, but also this regularization. So, for example, you have something that's doing these sparse byte writes, for example. They will just accumulate, if you like, in the cache until some point that they get written back. The key thing is that proxy cache is coherent to the rest of the system. And so any transaction within the system that is accessing that same address space that's cached in the proxy cache will cause that proxy cache to be written back or updated or whatever. It will be kept current because it's part of the coherency system. Similarly, there's another cache within the interconnect, the SMC or system memory cache, which is a cache on the interface to the external memory. So effectively, this is a system-level cache per memory interface. Again, it's configurable up to 8 megabyte, which doesn't sound very much for that, but remember that this is per memory interface, and typically the larger devices have multiple interleaved interfaces, 4, 8, even 16 in the large systems. And both of these caches can be configured with ECC or parity if you're building a functionally safe system. So I want you now to get on and talk about the main thing of this talk, which is the data transport for AI applications. So coherent NoCs are all required when you share data with the CPU, either between CPUs or between I/O devices and the CPUs. And as I said, these always work on 64-byte coherency granules. But you have extreme bandwidths in these AI and ML devices, AI and ML accelerators. We heard in an earlier talk about using local memories to reduce traffic. But the key thing here is to separate shared and non-shared memory traffic. So a software guy always want to say everything is shared, all memory is the same. Everything goes through coherency and everything will work, but the reality is that in these systems it will work very slowly. So you need to provide separate paths for shared traffic and non-shared traffic, and provide a fast and wide path to memory for the non-shared traffic. So the solution here is to combine the coherent NoC for data that's shared with CPUs with just an IO coherent or non-coherent NoC for the optimal bandwidth and performance. So the coherent hub, effectively, will be close to the cache CPUs. Narrower buses, ours generally works on 256-bit buses. And then the wide NoC connects to the rest of the system. And because of the repetition of these AI accelerators, a mesh technology can be appropriate for many AI applications. So instead of having these kind of big wide buses, you have a mesh architecture. It works when the blocks are regular and where they will therefore fit within the mesh. And that's not always the case. And so mesh is not always the right answer for every system. Some systems are irregular. But for regular designs, then the mesh isn't a good option to consider. So we have the Encor 3 for the coherent part and the FlexNoC for the rest of the system. So the FlexNoC XL, XL is the extra large, or the one that's really aimed at AI applications, is addressing the bandwidth requirements of these systems. So it supports up to 2048-bit wide connections, over 200 network interface units, and supports virtual channels for quality of service. So this is why it's really a different thing to the Encor. The Encor, it's working on 64-byte cache lines, which is 512 bits. Going more than a cache line is inherently very, very difficult. So what we do here is separating into the two systems where possible. There's one feature in the FlexNoC NL which is particularly aimed at AI, which is the broadcast write. So you have the ability to instantiate broadcast stations throughout the NOC. And the broadcast station is like a repeater cell. So you perform a write to the first broadcast station, and that will then send multiple writes out to lower down subservient broadcast stations. And you can have as many of those as many levels as you like within the NOC, and then they will write the data to multiple endpoints. So the idea of this is where you have a system where you have to update multiple endpoints with the same data. For example, you're writing DNN weights or image map updates, or you're sending AI system commands. You can send the same data or the same command to multiple devices simultaneously with one write. And if you can put these broadcast stations lower in the network hierarchy, then they use less bandwidth in the system. As I mentioned, these systems will have large numbers of memory bandwidth, so they have large numbers of memory controllers, and so we can have 8 or 16 memory channels interleaved. There's reorder buffers to reassemble in the correct order if they arrive out of order, and up to 1,024-bit wide connections, and also support non-power of 2 interleaves. So you can interleave, it says here 8 or 16 channels, you can have non-power of 2, so you can have 10 channels or 12 channels, however many channels as you like, with the FlexNoC. So the other aspect to consider, change in tack a little bit, is building and assembling a system. So one approach is to build your own interconnect, and people do. And in a way, it doesn't sound terribly difficult. Where it gets really difficult is when you get to the stage where you don't quite have what you want, it doesn't meet PPA, it doesn't meet timing, doesn't get the area, then you get an iterative situation. And iterating a custom design can be very, very difficult and can lead to a situation where you have a kind of almost undefined amount of effort to finalize the project. So with our tools, we have an EDA tool that allows you to very quickly define your NOC, configure all the things you want to do, and generate the RTL scripts, the documentation for it. And you can quickly refine that by making changes very, very quickly, as opposed to changes would be very painful if you was doing it in a custom NOC that you built yourself. I mentioned earlier on about the mesh topology, and that is physically aware within the tooling as well. So within the tooling, you can define the layout of the physical layout of the design you want to have. I mentioned about putting the blocks within the mesh, and so the tools are physically aware, so it helps you to achieve timing and area and power PPA targets quickly. I mentioned that a lot of designs that we seem to get involved with are automotive. The point here is that cache coherency is required in safety-critical designs, and it's a tricky subject to get right. So Encor, the current interconnect, is actually certified by Exceeder as an ASIL-D, functionally safe interconnect. And we also have the ability to add resilience to the FlexNoC as well. So you can add ECC or parity on interfaces, on all the RAMs within it, and you can also have things like directory duplication. Links can have ECC or parity as well. There's various different things you can configure, both in Encor and in FlexNoC. So to summarize then, our kind of solution or our realization was the need to separate coherent traffic from high bandwidth AI traffic and have different paths to memory. FlexNoC 5 enabled us to have this wide buses, the mesh topology and broadcast rights for AI, and the tooling helped to speed designs, and the ISO 26262 certified ASIL-D for Encor and FlexNoC 5 resilience helped in automotive applications, which we have been involved in. And finally, I didn't mention this, so it shouldn't really be on the summary, but I just want to say that we're aware chiplets will offer additional optimization opportunities in the future. Not really ready to talk about that just yet, but maybe next year that'll be something we can talk about. But particularly in automotive and AI, it may be an important thing going forward. Thank you.